Okay, so in the last video we started talking about wave behaviors and we talked about reflection. In this video we're going to talk about the concept of refraction. Okay, so before we get to refraction, just to recap really quickly, here we're looking at the ray picture of a wave, and the instant wave here, in this case this is a light ray, so it's an electromagnetic wave. Instant basically means like incoming. Okay, so here you can see the instant light ray comes in and it strikes what's called the boundary. Okay, and a boundary is basically the separation between two media, two different substances that waves can travel through. So in this case, the two media are air and glass. Okay, so this line that I just drew here, that's the boundary line, and then the imaginary line perpendicular to that line is what's called the normal. Okay, remember normal means perpendicular. And when you're doing problems with reflection and refraction, you always measure the angles with respect to the normal. Okay, so we already talked about how for reflection, we're talking about a wave hitting a flat surface and reflecting off the flat surface. You say that the angle of incidence, let's say theta I, is equal to theta reflect. And so here you can see these two angles are equal to each other. Okay, now when we talk about refraction, the angle of incidence and the angle of refraction are not the same thing. Okay, so you can even see here in this picture how this angle down here is different than the angle of incidence up here. Okay, so we're about to start talking about refraction, not to be confused with diffraction, which is a completely different thing. Alright, so let's get into it. Okay, so imagine you have a situation where a wave is traveling from one medium to another. Okay, now what can happen in that situation is the wave can bend. And this is what is known as refraction. Okay, so why does the wave bend when it goes from one medium to another? Well, basically what happens is when the wave goes from one medium to another, the wave speed actually changes because, you know, the speed of a wave depends on what the wave is actually traveling through, what substance the wave is traveling through. And so when you go from one type of medium to another type of medium, based off of the characteristics of the two media, you could have a change in wave speed. And that change in wave speed causes a change in wavelength, which causes a bend. Okay, so here's an example. Okay, so let's say you have two media, clear water and muddy water. Here's the boundary line between them. And let's say you have a wave come in. You can see the wavefronts shown on the left. Okay, and so you're going to see the refraction, the bending, when it goes from the clear water to the muddy water. Okay, so now these green wavefronts represent the refracted wave. And notice you can tell looking at the wavefronts that the wavelength is actually smaller in the muddy water than it is in the clear water. And that's because the muddy water is harder for the wave to travel through. Okay, so this is what's known as refraction. Okay, because the water wave moves slower in the muddy water than it does in the clear water, that causes a change in wave speed, it causes the wavelength to also decrease, and it causes the entire thing to kind of bend. Okay, and so this is what's called refraction. Okay, the bending of a wave traveling from one medium into another. Okay, so in case you're not convinced as to why that would cause a bend, okay, we'll do another example in just a second. Here, the arrows you just saw added are just the rays for these two waves. Okay, remember, typically when you're doing problems with refraction, normally you look at the rays and not the wavefronts, but I have seen questions involving both. Okay, so just remember, waves and wavefronts are two ways. Sorry, rays and wavefronts are two ways of looking at waves visually. And there's a normal. Okay, so notice that the angle of the incoming wave, the incident wave, that angle theta incidence is measured with respect to the normal line, and then the angle of refraction is also measured with respect to the normal line. And so notice in this situation that theta refraction is actually a smaller angle than theta incidence. Okay, now something important you need to know about refraction is that number one, refraction, everything we're talking about in 4.4 applies to any type of wave. Okay, sound wave, water wave, light wave, whatever. Okay, so refraction is a wave behavior which occurs when a wave travels from one medium into another medium and changes speed, causing the entire wave to bend. Now, something that's important for you to know is that during refraction, the speed of the wave changes and the wavelength also changes, but the frequency of the refracted wave remains the same. Okay, and so that's important to keep in mind because frequency remains the same during refraction. That basically means if you think of the wave equation, v equals lambda times f, during refraction, if you know that f is fixed, okay, that basically means that the ratio of v over lambda also has to be a fixed value. Okay, so in other words, if you have a wave go from one medium into another medium, if the wave speed increases, in order for this ratio to be constant, right, if v goes up, lambda would also have to go up. And if v goes down, lambda would also have to go down. So it's like in the last slide where we saw the wavelength of the water wave going from clear water to muddy water. In the muddy water, the wavelength shrunk because the wave speed also decreased in the muddy water. Okay, and the reason again for that is that frequency of a wave during refraction is constant. Okay, so again, everything we're talking about in this unit applies to any type of wave, but we're mainly going to look at refraction in terms of electromagnetic waves, specifically light waves. Okay, now in case you're still not convinced as to why the bending happens, here's a good example. Okay, so imagine the ranks of a marching band. And let's say you got the members of the marching band, they're all in line, they're walking along the concrete, everybody's happy, da-da-da-da-da. Okay, and then what's going to happen is this guy down here is about to hit the mud. Okay, now when this guy down here hits the mud, this guy down here all of a sudden starts to move slower. Okay, why is he moving slower? Well, because it's hard to walk in mud than it is in concrete. So this guy over here is going to slow down while everybody else in line is still on the concrete and they're all walking at the same speed. Okay, so watch what happens. Okay, is the next step, this guy doesn't move as far, everybody else moves a lot farther, and so it causes a kink in the line. Okay, and then as time goes on, more and more people start entering the mud. The kink gets bigger and bigger and bigger. Notice that the spacing between the ranks gets smaller because now the members of the marching band can't move as fast. Okay, and so what you see here is basically refraction. Now the cadence doesn't change, the frequency of the wave doesn't change, okay, but the wave speed changes, which causes the wavelength to also change. Okay, because the individual members of the marching band can't walk as fast, okay, that means that they basically get spaced closer together on the left side relative to the right side, okay, and that causes that bending, and that causes this refraction effect. Okay, so hopefully that helps you understand the concept of refraction a little bit more. Alright, so moving on. We talked about this before. It should be clear that the incident wave is faster than the refracted wave in this example. Why is this? Again, you can tell just visually. Remember, when you're looking at wavefronts, the lines that represent wavefronts represent the crests or the compressions of that wave. And so you can see the green wavefronts are closer together, meaning that the green ones have a smaller wavelength compared to the red wavefronts. And remember that the ratio of f equals v over lambda, that ratio is fixed, and so smaller wavelength means smaller speed. And again, conceptually we talked about how it's harder for water to travel through muddy water than clear water, which is why it also makes sense that the wave doesn't move as fast in the muddy water. Okay, so let's talk more about this bending. Before we do that, just really quickly, this is an IB question from a couple years back. And the question says a water wave entering a harbor passes suddenly from deep to shallow water. In deep water, the wave has frequency f1 and speed v1. In shallow water, the wave has frequency f2 and speed v2. Which of the following compares the frequencies and speeds of the wave between deep water and shallow water? Okay, so remember, the wave behavior involved when a wave goes from one medium to another medium and changes wave speed and wavelength is refraction. Anytime you have refraction, the frequency remains fixed. Okay, if you know that one fact, you should be able to tell right away that C and D are not viable answer choices. Okay, now between A and B, remember because of the wave equation, V equals lambda times F, if you know that F is a fixed quantity, okay, that means it has to be the same ratio for any value of V and lambda. So in other words, F1 would have to equal V1 over lambda 1, and F2 would have to equal V2 over lambda 2, but because the frequency is fixed, that also means V1 over lambda 1 has to equal V2 over lambda 2. Okay, so let's think about this. We can tell visually that the wave speed V2, the wavelength in the shallow water is less than the wavelength in the deep water, just based off of the spacing between the waves fronts. Okay, remember the spacing between the wave fronts is the wavelength. So here is lambda 1, here is lambda 2, because lambda 2 is smaller than lambda 1. Okay, that also means that the wave speed of V2 has to be less than the wave speed of V1. Okay, so that means the answer would be A. In other words, when it goes from the deep water to the shallow water, the wavelength gets smaller, and therefore the wave speed also has to get smaller. Alright, so moving on. Okay, now what are some examples of refraction? Well, there's lots of interesting examples of refraction, actually. If you've ever seen this optical illusion where you put a straw in a glass of water and it appears to bend, the reason the straw looks bent, obviously it's just an optical illusion, but the reason for that is because the light rays bend at that air-water interface. There's a separation between air and water right here. There's a boundary. Okay, because there's refraction happening there, the light rays are bending. That causes the straw itself to look bent. Okay, and so that's definitely an optical illusion. If you take the straw out, it looks perfectly normal, but that's why it appears bent. Other examples of refraction in everyday life, if you ever go fishing, if you try to go spear fishing, and you're looking at the fish in the river and you're trying to, poke it with a spear to catch a fish, the position where the fish is actually different from where it appears, because when you're looking into the water at an angle, the light ray bends, and therefore you might see the fish in one location, but if you try to poke it with a spear, you're going to miss because the fish is actually in a different location. Okay, so that's another example of refraction. Rainbows are also caused by refraction, actually a combination of a variety of wave behaviors, one of which is refraction. Basically because when light from the sun goes into raindrops, it bends, and as it bends around the raindrop, it kind of reflects off the inside of the raindrop and then comes back out and forms a rainbow. We'll talk more about that later. Any type of lens, whether it's your eyeglasses, microscope, telescope, anything like that, that involves refraction. Okay, so if you wear eyeglasses or if you wear contact lenses, those are basically designed so that when light goes through those lenses, it bends and it lands correctly on your retina. People that have normal vision, so basically your eyeball has a lens inside of it, and so people with normal vision, when the light goes in, it goes through the lens in their eye, and it refracts and it hits their retina. Okay, well, if you've got vision issues, if you're nearsighted or farsighted, if you wear glasses or contact lenses or something like that, then basically there's something wrong with the lens in your eyeball, and so the light doesn't actually hit your retina perfectly. And so you need an extra set of lenses to cause the light to bend just in the right way so that you can see correctly. Okay, so anything involving any type of lens is an application of refraction. And fiber optics, we'll talk more about fiber optics later, but that's another example of refraction. Okay, example. What wave behavior is being demonstrated here? So let's see that one more time. What wave behavior do you think this is? Okay, that is definitely reflection. That's an echo from a wall. Okay, so I'm going to skip to refractive index. Okay, and we'll see where refractive index plays a role when we talk about Snell's law. For now, add this to your notes. Okay, so we talked before about how refraction is caused by a change in wave speed and wavelength as a wave tries to go from one medium into another medium. And so let's quantify this a little bit. Okay, let's introduce the concept of refractive index. Now the symbol for refractive index is n. Okay, that's lowercase n. Now it doesn't have to pertain to refractive index of a light wave, but that is typically how we're going to see it in this class. Okay, so here's how refractive index of a light ray is defined. Okay, the refractive index of a substance n is equal to the ratio of c, which is the speed of light in a vacuum, to v, which is the speed of light in that medium. Okay, so for example, let's say the medium was a vacuum, so let's say no air, you're just out in space, you measure the speed of light, it happens to be the same as c, because c is the speed of light in a vacuum. That would give you a refractive index of 1. Okay, so basically n in a vacuum is basically equal to 1. Now, what are the units for refractive index? Well, c is in meters per second, v is in meters per second, so refractive index is unitless. I will also tell you that for the purposes of the IB exam, the refractive index of air is also assumed to be about 1. Again, no units. That's not something that you're given necessarily, but that's something, just a factual piece of information that you need to know. In other words, in air, light basically travels with the same speed as it would in a vacuum. Okay, so refractive index quantifies how quickly a wave can move in one medium compared to another medium. So in the case of light, you can never have a refractive index that is less than 1 because the fastest light can ever move is c. Okay, so let's say I tell you that the refractive index for, I don't know, glass is 1.5. What does that mean? Well, basically that means that light is 1.5 times slower in glass than it is in a vacuum. Okay, so the higher the refractive index, the slower the wave moves in that medium. Okay, so make sure you understand how refractive index is defined. Okay. Now here we see in the notes a refractive index Nm is often used when dealing with light waves. It is defined to be the ratio of the speed of light in vacuum C to the speed of light in the medium Vm. We already talked about that before. Normally you'd be given at least one refractive index of a material. If you were like an engineer or something, you would like look these values up in a table. It basically varies depending on the type of material you're talking about. Vacuum and air is about 1. Water is about 1.33. Acetone has a refractive index of about 1.36. Quartz, crown glass, diamond has a very high refractive index, which is one reason why diamond is so shiny. We'll actually talk more about that later. That's basically because when you go from air into diamond, or from diamond to air, there's a lot of bending involved by those light rays. That's one reason why diamonds appear so shiny. We'll talk more about that later. Okay, so there is an equation here, and I'll talk about this equation momentarily, but this equation that you see here is basically what's called Snell's law. Okay, so that's going to be our main equation for doing calculations with refraction. Okay, so before we get to that, let's do a quick example with the definition of refractive index. The index of refraction for a particular glass is 1.65. What is the speed of light in the glass? Okay, well, the speed of light in a vacuum is 3 times 10 to the 8 meters per second. So, by definition, the refractive index of the glass is C divided by the V, the speed of the light in the glass. And so V glass would just be C over N glass, which would be 3 times 10 to the 8 divided by 1.65, which would be about 1.8 times 10 to the 8 meters per second. Okay, still plenty fast, but quite a bit slower than it is in a vacuum. Okay, so, and keep in mind that C is a constant that's given to you in the data booklet. Okay, so just a real basic example with the definition of index of refraction. Okay, so let's talk about Snell's law. So we've kind of seen this before that, when a wave goes from one medium to another, it bends, and that bending we've talked about that is due to change in wave speed and wavelength, yada, yada, yada. Okay, now there's a way to quantify the amount of bending, and this is where we have something called Snell's law come in. Okay, here's how I learned Snell's law, and this is how I prefer to think of Snell's law. This equation down here, that is not how it's given to you in the data booklet, but that is how I would think of Snell's law. I believe in the data booklet they give you this first equation. Okay, but it basically ends up being the exact same thing, just kind of rearranged. Okay, in Snell's law, you have N1 sine theta 1. So imagine you're going from medium 1 to medium 2. So N1 is the refractive index of your first medium. Theta 1 would be the angle of incidence, and that's equal to N2, which is the refractive index of your second medium, times sine of theta 2, where in this case theta 2 would be the angle of refraction. Okay, so remember, angle of incidence, angle of refraction. Keep in mind, by the way, that these two angles must be measured with respect to the normal. When you're doing these calculations, please make sure that your calculator is in degree mode. Okay, so write that down in your notes, and let's do some examples before we end this video. Okay, so I'm just going to skip a little bit. Okay, and I want you to take a look at the simulation. Okay, so here we have a Snell's law simulation. And here at the top you can see this medium up top is air. And down here, the second medium is water with a refractive index of 1.33. And if I wanted to, I could take a protractor and I could actually measure these different angles with respect to the normal. Okay, but we're talking about Snell's law. And so if I write out Snell's law, N1 sine theta 1 equals N2 times sine theta 2. Let's say, experimentally speaking, let's say I don't know what N2 is. Okay, so let's say N2 is an unknown, but N1, let's say the top material is air, and so that has a refractive index of 1. Okay, I can easily measure theta 1. That would be this angle right here. Remember, you always measure with respect to the normal. So this would be the angle of incidence. Theta 2 would be the angle of refraction. Okay, and so if I wanted to calculate N2, I could very easily do that. I would just do N1 times sine theta 1 divided by sine theta 2. And so in this case, N1 is air. Sine theta 1, I would look at my protractor. I don't know that it's perfectly aligned. Try to do the best I can. Okay, but that angle looks to be about, let's see, I guess about 40 degrees. So sine 40 degrees divided by sine of theta 2, which is the angle of refraction. That looks to be, it's kind of hard to read, maybe 28 degrees. And it's going to be a little off because there's some uncertainty in this measurement, of course. But practically speaking, you could use this type of setup to measure different indices of refraction if you wanted to. I'm going to type that in my calculator and just see what I get. I actually get a refractive index of 1.37. The simulation is telling me it's 1.33, so that's pretty close considering I just kind of quickly eyeballed those two angles. Okay, so this is basically how Snell's law works. Okay, it relates the two indices of refraction and the angle of incidence and the angle of refraction. Okay, so I will put a link to the simulation so you can see how that looks. This just shows you basically the exact same visual. And just to do a really quick example, a beam of light travels from air, which has a refractive index of 1, into an optical fiber, which has a refractive index of 1.44. The light is incident on the fiber at an angle of 22 degrees. The first question says determine the speed of light within the optical fiber. Okay, well, the fiber has a refractive index of 1.44, meaning that N fiber is 1.44, and by definition that is the speed of light in a vacuum divided by the speed of light in the fiber. So in other words, V fiber is equal to 3 times 10 to the 8 divided by 1.44, and I can put that into my calculator and find out how fast light is moving in my fiber. Okay, and I get about 2.08 times 10 to the 8 meters per second. So that's my first question there. Calculate the angle of refraction for the light within the fiber. Okay, so if I want the angle of refraction, if I think of Snell's law, that's basically theta 2 in Snell's law. And so I can easily plug into Snell's law. So here's Snell's law, N1 sine theta 1 equals N2 sine theta 2. N1, if it's air, it's not going to tell you in IB questions that air has a refractive index of 1, but that's just something that you need to know. So that would be 1 times sine 22 degrees equals 1.44 times sine theta 2. Okay, so theta 2 would be equal to the inverse sine. It's inverse sine because theta 2 is stuck inside a sine function, so I have to do an inverse function to get rid of that sine. So the inverse sine of sine 22 degrees divided by 1.44. Okay, and if your calculator is in degree mode like it should be, when you do the inverse sine of sine 22 divided by 1.44, you should get 15.1 degrees. Okay, so the angle of refraction here is 15.1 degrees. Alright, so pause there and look at that for just a second. The last thing I'm going to leave you with is I wanted to show you what this looks like on a simulation. Okay, so I'm going to erase this. Okay, so keep these values in mind for just a second. 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . 1.44 . Let me go back. Okay, 1.44 and then 22 degrees. Okay, so let's say we have an index of refraction of 1.44 and the angle of incidence is 22 degrees. Okay, so let's say that's 25, so 22 is somewhere around here. So notice in this situation that basically this is theta 1, this is theta 2. Okay, and actually notice that theta 2 is smaller than theta 1. Okay, so as a general rule of thumb, when you're going from a lower refractive index into a higher refractive index, what you would say is that the refracted ray bends towards the normal. In other words, here is the incident ray up here, the refracted ray is down here, and it is bent towards the normal compared to the original light ray. Okay, so when you're going from a lower refractive index to a higher refractive index, it bends towards the normal, which is the same thing as saying that the angle of refraction is smaller than the angle of incidence. And if the opposite is true, if you're going from a higher refractive index to a lower refractive index, then it bends away from the normal. So let's say we're going from the fiber with a refractive index of 1.44 into air. Okay, now if you look at this, notice that here's theta 1, here's theta 2, always measured with respect to the normal. Notice that here theta 2 is bigger than theta 1 because we're going from a higher refractive index to a lower refractive index. Okay, the ray bends away from the normal after it refracts. Okay, so in this video we talked about the concept of refraction, we talked about the definition of refractive index, Snell's law and how you can use Snell's law to do basic calculations involving refraction, and then the idea that based off of whether the refracted ray is bending towards or away from the normal, you can figure out which medium has a higher refractive index. Okay, because if it's bent towards the normal on the refracted side, that means you're going from a lower to a higher refractive index, and if it's bent away from the normal, then it's switched. Okay, so the last thing is I just want you to try to do example 2 on your own. Okay, it says the beam of light from the previous example reaches the end of the fiber and exits into air. If the angle of incidence on the end of the fiber is 30 degrees, calculate the angle of refraction outside the fiber. Sketch the situation above and comment on the direction that the refracted light bends. And then see how your answer to the first question would change if the angle of incidence was 50 degrees and not 30 degrees. So try to answer example 2 on your own. We will talk about example 2 in the next time I see you guys, but for now you should be able to do problems involving refraction on your practice worksheet. As always, please let me know if you have any questions, and I'll see you guys in the next video.